Welcome to Conversations with AI. In this episode, we asked Google's Bard some tough and interesting questions about energy, matter, and the cosmos. How smart is Bard when it comes to physics? Listen and find out.
Matter can be converted into energy in an atomic explosion. Under what circumstances can energy be converted into matter?
Sure, I can help you with that. Matter can be converted into energy in a process called nuclear fusion. In nuclear fusion, two or more atoms are combined to form a heavier atom. This process releases a large amount of energy, which is why it is used in nuclear weapons and power plants. Energy can also be converted into matter in a process called pair production. In pair production, a high-energy photon is converted into an electron and a positron. This process is very rare, and only occurs in the presence of a strong electric field. The conversion of matter into energy is described by Einstein's famous equation, E equals mc squared, where E is energy, m is mass, and c is the speed of light. This equation states that mass and energy are equivalent, and that one can be converted into the other. The conversion of energy into matter is a much more difficult process, and only occurs in very rare circumstances. However, it is possible, and has been observed in laboratory experiments. I hope this helps.
I've heard that at the Big Bang, there was only energy as the temperature was too hot for matter, but when the new universe expanded enough to cool down, matter began to condense. Does anything like this occur in the current universe?
Yes, the process you're describing is called recombination. At the Big Bang, the universe was incredibly hot and dense, and filled with a plasma of ionized particles. As the universe expanded and cooled, these particles slowed down and were able to recombine into neutral atoms. This process began about 380,000 years after the Big Bang, and by the time the universe was about 500,000 years old, most of the hydrogen and helium in the universe had recombined into neutral atoms. This allowed light to travel freely through the universe for the first time, and it is this light that we see today as the cosmic microwave background radiation. Recombination is still happening today in very small pockets of the universe called hydrogen-2 regions. These regions are filled with hot, ionized gas, and they are found around young, massive stars. The ultraviolet radiation from these stars ionizes the gas in the hydrogen-2 region, but as the gas expands and cools, it is able to recombine and emit light. Recombination is an important process in the universe because it allows light to travel freely. Without recombination, the universe would still be opaque, and we would not be able to see the stars and galaxies that are around us.
The inside of our sun is all plasma that is hot enough for fusion to create energy from matter. When that produced energy is released, does it not expand and cool and recondense into matter?
No, the energy released from the sun does not expand and cool and recondense into matter. The energy released from the sun is in the form of photons, which are particles of light. Photons are massless, so they do not have any mass to cool or condense. The energy released from the sun travels through space as electromagnetic radiation. When this radiation reaches Earth, it is absorbed by the atmosphere and the surface of the planet. The absorbed energy is then converted into heat, which warms the planet. The heat from the sun is what drives the Earth's climate system. The heat causes the oceans to evaporate, which creates water vapor in the atmosphere. The water vapor then condenses into clouds, which can produce rain or snow. The heat from the sun also drives the wind patterns on Earth. So, while the energy released from the sun does not directly recondense into matter, it does play an important role in the Earth's climate system.
What was the form of primordial Big Bang energy if it was not electromagnetic?
The exact form of primordial Big Bang energy is still a matter of debate among scientists. However, it is generally accepted that it was not in the form of electromagnetic radiation. This is because electromagnetic radiation is a type of massless particle, and massless particles cannot exist at temperatures as high as those that were present in the early universe. One possibility is that the primordial Big Bang energy was in the form of scalar fields. Scalar fields are hypothetical fields that are associated with fundamental particles, such as the Higgs boson. Scalar fields can exist at high temperatures, and they could have played a role in the early universe. Another possibility is that the primordial Big Bang energy was in the form of gravitational waves. Gravitational waves are ripples in spacetime that are caused by the acceleration of massive objects. Gravitational waves have been detected indirectly, and they could have been present in the early universe. It is also possible that the primordial Big Bang energy was in a form that we do not yet understand. Scientists are still working to learn more about the early universe, and it is possible that they will one day discover the true form of primordial Big Bang energy.
Is there a definition of temperature that doesn't involve electromagnetic radiation or its effect on matter?
Yes, there are alternative definitions of temperature that don't involve electromagnetic radiation or its effect on matter. One such definition is based on the concept of entropy. Entropy is a measure of the disorder or randomness of a system. In a system with high entropy, the particles are arranged in a more disordered way, while in a system with low entropy, the particles are arranged in a more ordered way. According to the entropy-based definition of temperature, temperature is a measure of the average kinetic energy of the particles in a system. The more kinetic energy the particles have, the higher the temperature. This definition is consistent with the fact that hotter objects radiate more electromagnetic radiation than colder objects, since hotter objects have faster-moving particles that are more likely to emit photons. Another alternative definition of temperature is based on the concept of statistical mechanics. Statistical mechanics is a branch of physics that deals with the behavior of large numbers of particles. According to the statistical mechanics definition of temperature, temperature is a measure of the likelihood of a particular arrangement of particles. The more likely an arrangement is, the lower the temperature. This definition is consistent with the fact that colder objects tend to be in a more ordered state than hotter objects. Both the entropy-based definition and the statistical mechanics definition of temperature are equivalent to the traditional definition of temperature based on electromagnetic radiation. However, these alternative definitions provide a different perspective on what temperature is and how it is related to the properties of matter.
Both of you examples of entropy-based temperature involve particles and kinetic energy. How can this be defined in an environment where particles are impossible?
The concept of temperature and its association with entropy and kinetic energy are fundamentally linked to the existence of particles and their interactions. In an environment devoid of particles, these concepts lose their traditional meaning and require a different approach to define temperature. In a particle-less environment, the traditional definition of temperature based on the average kinetic energy of particles becomes inapplicable. Similarly, the entropy-based definition, which relies on the degree of disorder or randomness among particles, also becomes irrelevant. One alternative approach to defining temperature in a particle-less environment could be based on the properties of spacetime itself. Spacetime, the fabric of the universe, can exhibit certain characteristics that could be used to define temperature. For instance, spacetime can be curved and distorted, and these distortions could be quantified to represent temperature. Another possibility is to define temperature based on the behavior of hypothetical fields, such as scalar fields or gauge fields, that permeate spacetime. These fields could possess properties, such as energy density or fluctuation patterns, that could be used to define temperature. It is important to note that defining temperature in a particle-less environment is a challenging and speculative endeavor. The absence of particles requires a fundamental rethinking of temperature and its relationship to entropy and other physical concepts. As our understanding of physics expands, particularly in the realm of quantum mechanics and gravity, new insights might emerge that provide a more comprehensive definition of temperature in particle-less environments.
So, what I'm hearing is that, at the Big Bang there was no matter in the bang but only an expansion of a spacetime singularity, true?
Yes, that is correct. At the very beginning of the Big Bang, there was no matter in the traditional sense. The universe was in a state of incredibly high energy density and temperature, and the conditions were not suitable for the formation of matter. Instead, the universe was filled with a dense plasma of fundamental particles and energy. As the universe expanded and cooled, the conditions became suitable